Hello, welcome to the trenches of cosmology. I am not full screen, so I will fix that. Good. Right. I am Sean Hotchkiss, and I am a part time cosmology researcher and part time doer of things like this. Trenches of Cosmology, we aim to show you what is happening in the trenches of cosmology. So, not just the nicely packaged stuff that's ready for a documentary, and not just stuff that people already know to find interesting, like black holes, warp drives, etc., but the stuff that cosmologists themselves find interesting and want to solve, and the ideas they come up to solve them. Uh, because that is interesting enough all on its own, and it's the actual stuff that we're working on, not just what sounds exciting. Having said that, what we're talking about today is a mirror dark sector, which would look exactly like uh, the real world. I mean, not exactly like, as in we wouldn't have a dark Sean live streaming on the dark trenches of cosmology, but there would be dark planets and dark galaxies and things like that, which is pretty cool. So, yeah, that's a real treat for today, which I'm pretty excited by. Um, what I usually do as people drift in is just start by giving overviews of some recent papers that have been talked about a lot in cosmology journal clubs. So I will start with that again. I'm going to try, I say this every single time I do a live stream, I'm going to try and keep that really brief so that, first of all, our minds don't get tired. And second of all, so that we um, have time to do the main content. So let me share my screen and hopefully do it correctly. Yeah, Bo. As per usual, it'll take half an hour, and I'll say I'm wrapping up for the whole half hour. Okay, let's see. Is this why does it happen? Okay, and then I want me to be this little thing in the corner, but I want you to be that. Boom. I think that's what I wanted. Didn't want it to be blurry. How do I make it not blurry? Maybe I'll undo it and then do it again. That's still blurry. That's very strange. Maybe I have to start sharing again. This is very frustrating. Okay. Let me stop sharing and start sharing again. I presume that's blurry to everyone and not just me. Ah, that's better. Awesome. Okay. So, as per usual, I have to warn you that this is the most popular, as you can see here, papers. And it's gone blurry again. Okay, this is. I'm not sure how to fix this. Is it blurry on your screen, or is it just blurry on mine? No, it is blurry on everything. What? What? Okay. Um, I might just have to talk about it without that in the background then. This is frustrating. Okay. I'll try one more time. And then if it goes blurry again, I'll just have to ask the people at HAPS in the future what I'm doing wrong. And not do it next time. Right. Okay. At least it's not blurry at the moment. So maybe I've just got too many windows open. As I have to warn everyone every time, these are the most popular in kind of all of extragalactic physics, which is includes cosmology, but also includes stuff that is more about how galaxies work. So I'm not an expert on a lot of this, and I've actually spoken to the people at Benty Fields, and apparently there'll be an update in a few weeks where I can actually cut out all of the extragalactic stuff. So then I would not have to show you these exciting titles and then not tell you anything about them. Yes, David, hello. Was reading a popular press discussion of recent findings suggesting supersymmetry may not hold and discussing entropic gravity. Yeah, I mean, supersymmetry is a very compelling idea and may very well be true. but there's no absolute guarantee it's true. On that topic, I think when supersymmetry was first being postulated, it was supposed to do a couple of things. One was it would solve this thing called the hierarchy problem, which is kind of it's got to do with the mass of the Higgs boson. And let me just share your comment on the screen. Present on screen. The mass of the Higgs boson and the supersymmetry. Have I done that? Everything's. Oh yeah, cool. This added symmetry, which was called supersymmetry, between things called fermions and things called bosons. Fermions are things like electrons and the quarks. Bosons are things like photons and other force carrying particles, like W and Z bosons, which maybe people don't know about, but the W and Z carry the weak force. Gluons carry the strong force. In any case, there was a symmetry between them, and what that symmetry would do, I mean, amongst a lot of other things, but the reason it was useful for this thing called the hierarchy problem is that the mass of the Higgs boson should receive things called quantum corrections, which is basically by interacting with stuff like electrons, it should create an additional mass to the Higgs boson. And then it was suspicious that the Higgs boson's mass was so small because these corrections would be quite large. Now, of course, you could just say, well, it's a fundamental parameter, it could be anything, but these added terms should be there. So there would need to be some fine canceling between the added terms and like the raw God-given value for the Higgs boson. So what supersymmetry did is that every correction there was from a fermion was exactly cancelled by a correction from a boson because of this symmetry. And it was very exciting to people, in the 70s, or I might be getting my decades wrong because I wasn't a cosmologist at the time, but very exciting because it would have fixed this hierarchy problem. The hierarchy being, why is there a low energy Higgs mass rather than a high energy Higgs mass? But if supersymmetry had been the solution to this hierarchy problem, it probably would have been discovered by now by the LHC. I mean, it's still possible that it kind of alleviates the hierarchy problem, but doesn't fully solve it. And then there was another thing that supersymmetry did that was very exciting, which was the unification of the three forces: the electric force, the weak force, and the strong force. So the electric and weak force already kind of get unified, but then the electroweak force and the strong force aren't yet unified. But just like the Higgs mass would kind of receive corrections from interactions, so would these fundamental forces. And if you look at the strength of these forces as you go up to higher and higher and higher energies, the electroweak and the strong force actually kind of get closer and closer, but not perfectly close. And it seemed like when you added supersymmetry, they got even closer. And if you added supersymmetry such that supersymmetry kicked in at exactly this kind of Higgs mass scale, so I can see why people fell in love with supersymmetry these few decades ago, because it seemed to be solving quite a few things. In fact, it even provided a dark matter candidate, one of the kind of lightest supersymmetric particles. So for every particle, you had a supersymmetric partner. The electron had the I think what is there's really weird terminology. I think the electron has the sylectron, which is the supersymmetric electron, and then the top quark would have the supersymmetric top, and then the bosons had enos added on the end. So the W would have a weno and the gluon would have a gluino. But in any case, whatever the lightest supersymmetric one was, based on a certain symmetry added to supersymmetry, but reasonably compellingly added, it would be unable to decay. And so therefore it would still be out there, whereas everything else would just decay. All the other supersymmetric particles would decay into stuff we know and see. This other one would still be there. So supersymmetry would have solved the hierarchy problem for the Higgs mass, would have helped the unification of forces at higher masses, and had a very compelling dark matter candidate. I mean, it would have been probably a WIMP, a weakly interacting massive particle. Unfortunately, physics is an observational science, and so far none of those three hopes is turning out to be true. It doesn't mean it won't be, but it hasn't showed up yet. As for supersymmetry itself as a possible fundamental law of nature, there's no reason why supersymmetry has to kick in at these large hadron collider energy scales, the sort of tera electron volt energy scales. And so supersymmetry may very well be a fundamental aspect of the universe, but just at much, much higher energies that we currently can't probe and won't ever be able to probe. So, yeah, I mean, that's a interesting thing. And I'm not sure, entropic gravity is then, yeah, a little bit, I'm not entirely sure. I don't know enough about entropic gravity, I think, to know why there would have been a link between supersymmetry and entropic gravity. But maybe they were unrelated and they were just talking about those two different things. Um, yeah, I've gone blurry again, so I'm just gonna hide that. I think there's no point fighting with the blur. Stop presenting. Sorry about that. Yeah, I have to remember to ask what could have possibly gone wrong there. So, good question, David, and I'm glad I managed to answer it. And as I said, I'm always going to go, it seems, over time. So, the couple of things I wanted to talk about that I can still talk about, I think. Okay, if you can't see the papers, I don't think most of this is really interesting. There's one thing that I found really interesting, which is a paper called Using a Neural Network Classifier to Select Galaxies with the Most Accurate Photometric Redshifts. Okay, so let's unpack what that means. Let me just type it into the comments and then share it on screen so that even though I can't share my screen, everyone can see the text. Very clever, if I don't say so myself. Cool. So neural network classifier is jargon for machine learning, essentially. And photometric redshift is this way of measuring how fast a galaxy is receding from us that is not spectroscopic redshift. So spectroscopic redshift is the gold standard of measuring these recession velocities, where you look at either the absorption or emission lines, spectroscopic lines of atoms and molecules. So carbon will give off certain lines as its electrons are excited to certain quantum energy levels and then fall back down. Very specific frequencies get emitted by carbon, very specific frequencies get emitted by oxygen, water, blah, blah, blah. So if in these galaxies there are stars with these elements inside them, they'll be emitting those lines. And if there's dust in the galaxy with those elements in it, they will be absorbing those lines. So we can look at the light coming from a galaxy and find these exact spectroscopic lines and then line them up. And then we can see the Doppler shift to see exactly how kind of fast, how much of a redshift there has been, and therefore the recession velocity. Thank you very much, David, for the appreciate award. Um, Photometric redshifts, however, are looking at a more broadband frequency of the light emitted by a galaxy. So it's if you haven't been able to get a spectroscopic instrument to look at a galaxy, all you've been able to do is look at its intensity in certain bands. So you might have a quite wide band of frequencies, and you've seen how bright it is, and then another wide band here, another wide band here, where this is like the x-axis being frequency. And there are certain features that you might see in your photometric, sorry, in your light as a function of frequency emitted by a galaxy, but not these very fine spectroscopic features, just like a rise in some frequencies, a drop in others. If I was an expert in stellar astronomy, I'd be able to tell you what these features to expect are. But just believe me that I guess the one expects those features. Now, a photometric redshift is then, as you take these bands, let's say you only get 5 or 7 bands. So you've only got 5 or 7 numbers about this frequency versus intensity measurement from the galaxy. If you can see where one of these features happens, you can kind of have an estimate of the redshift. And instead of having a sub% estimate, so instead of having the redshift as 1.2 plus or minus 0.03, you might have 1.2 plus or minus 0.1. So it's a much less accurate redshift. Now, what papers like this are doing, and I think this is one of those situations where it's a perfect use of something like machine learning in cosmology or astronomy, I guess, is where, okay, we can kind of predict what these photometric light curves of, well, not, I don't, light curves not quite the right word, but intensity versus frequency things should look like based on our understanding of stellar astronomy. But we're not perfect. We might miss that, there's some interesting features that happen in some frequency ranges and some blah, blah, blah. And What they do here is they take the ones where there have been spectroscopic measurements, where we know the redshift really, really well, and then they tell their neural network, this is what the frequency is. Now, here's some photometric data from the same galaxy. And let's say that they have a couple of hundred or a couple of thousand such spectroscopic measurements. Then the neural network can be trained to be able to, using machine learning algorithms, say, okay, if you give me a photometric redshift, I've got my, black box algorithm, not quite sure how you're doing it, but I've analyzed it and I've worked out that this is um, probably what the redshift is given my photometric information. And the hope there is that it might learn from certain features that we're not thinking to know about and we don't understand, and therefore it's getting better photometric redshifts than we're capable of because it's been trained on the spectroscopic data. And of course, if we have the spectroscopic data, that's not helping us at all. So this is just a training set, and then you go out and you do it where you only have photometric information and your machine learning algorithm tells you the redshift is this. I know it. Okay, it's a black box again, so it's kind of like, have you made a mistake? We don't actually understand what you're doing. But because, at least as a cosmologist, because this isn't kind of fundamental, I'm okay with a kind of black box telling me the redshifts a little bit. You still have to be a little bit cautious. And I think, as I said the last time I was discussing machine learning in the context of astronomy and cosmology, I used the kind of metaphor of a AlphaGo at chess. Um, it it might play a move and you don't understand why it's a good move, and then you analyze it and you're like, okay, it was subtly weakening some piece somewhere, whatever. I'm not sure. I'm not a grandmaster at chess, so I can't give the metaphor too well. But you might be able to say, okay, why is this neural network able to do this photometric redshift better than us? What are the common features it's seeing? And then, okay, there's this kind of bump. No one had ever noticed that bump before. What is causing that bump? And then, so it might, rather than being used as a black box, it might just be kind of something that can be used to point us in the right direction for where there's new physics. So yeah, photometric redshift is a place where machine learning is being applied to cosmology relatively successfully and quite interestingly. Um, so Paul, why would you not be able to use spectroscopic based instruments on some of the galaxies? To get a spectroscopic, okay, so I'm not an observational cosmologist, so take what I'm about to say with a little bit of a grain of salt. But what is definitely true is it's more expensive and it's more difficult. Um, the reason why, which is the interesting answer to your question, otherwise I'm just dodging it, is you do need to have very fine grained redshift, right? Like you have to know, because you don't know where these spectroscopic lines are going to show up before you do the measurement, right? Because if you knew the redshift, you wouldn't need to do the spectroscopic measurement. So you need to measure the intensity at every single frequency, very, very fine grain. These lines are very narrow. That's why we can get such accurate redshift measurements. Whereas for a photometric one, you might only need 7 bins. And I think way back in the day, okay, I might be about to just like talk complete nonsense here, but I think way back in the day, the way these photometric redshifts were done were by putting like almost like cellophane filters in front of the telescope, and then it would only let light through of a certain color. And nowadays, of course, it's more sophisticated than that. But this is sort of what you're dealing with photometric redshift. It's a lot more simple. You just have your telescope and it just observes 5 times in 5 different frequency bands, and I can see as a theoretical cosmologist, if an observational cosmologist tells me that's easier than getting this fine-grained spectroscopic every single frequency, that seems believable. So hopefully that's satisfying, Paul. If it's not, let me know, and I'll try and get an observational, I guess, astronomer here to go into more details about how to do spectroscopic measurements. Cool. So yeah, so that's useful because photometric redshifts are a lot more easy to do and cheaper, and therefore you can do it to more galaxies. So you can. I mean, I'm pretty sure that within a decade or so, there will probably be photometric redshifts of almost every single galaxy that we can actually observe, and that won't be true for spectroscopic redshifts. So being able to do photometric redshifts better, first of all, if it's just a black box, okay, maybe that's okay. But second of all, if the machine learning tells us how to do it better by looking at why it's able to do the slightly better prediction, then that's just making us our own non-machine learning algorithms better. So I think that's an exciting thing. And there were a couple other papers, but that was more just H naught and stuff like that. So let's actually in 20 minutes get on to the main content. And I should stop trying to find excuses to go on for too long. All right, where are my notes? Here they are. So, as I teased in the title and I teased in my intro, what we're talking about today is the scientific papers have called it um, a mirror world. I'm not sure. I think that's the best term for it because mirror implies some sort of reflection, right? And if I'm left-handed in the real world, mirror me would be right-handed, and that's not what this is talking about. What this is talking about is a model that would involve having essentially dark versions. So some of the dark matter would be made up of this, but dark versions of electrons, light, so photons, neutrinos, protons, and it's implemented so that, well, okay, so in the context I'm talking about today, it's implemented because it helps with this Hubble tension. I think it's been implemented in the past by particle physicists for other reasons to do with solving the hierarchy problem. This actually, your question at the beginning, David, has now become super relevant. If supersymmetry doesn't solve the hierarchy problem, what might? And I'm not enough of an expert in particle physics to know why these mirror world models alleviate this hierarchy problem. But I do know that that's one of the reasons they were brought up, is that somehow having this proportion of the universe, of the dark matter of the universe being this dark atoms, helps with this Higgs mass problem. Again, if this is something that people find interesting, let me know, and I'll try and get a particle physicist to come and talk about why a mirror dark sector would help with the hierarchy problem. But we're talking about today in the context of the Hubble tension, and I'll get into what the Hubble tension is in a second for people who aren't familiar. But the consequence is that there would be all of this like dark. So there's dark matter floating around in the universe, but most of dark matter can't interact other than gravitationally, because we've observed that it kind of has these big diffuse halos around galaxies. It's not clustering inside the galaxy the way that ordinary matter does. And ordinary matter can do that because it interacts with itself. So it sort of loses energy and falls in more. Whereas the dark matter, it falls in, but then it has a velocity as it falls in, and then it sort of just comes back out the other side and it orbits in this much more diffuse halo rather than getting clustered in the center. But that doesn't mean that some fraction of the dark matter can't interact. And so if there was this dark mirror sector meaning like piece of the universe. I think it's a particle physics jargon that I'm slipping into, but dark. Yeah, sector. Okay, I'll keep using the word sector. Sector just means piece of the dark matter pie. If it was doing all of the stuff that the ordinary matter does, but just not. When I say doing all the stuff with like the ordinary matter does, I mean in its own dark universe, right? So it is interacting with dark light. It's not interacting with our light. Then you would have dark planets, and you would have dark galaxies, and you would have dark stars, and all of these things would be out there in the universe emitting dark photons and all of this sort of stuff, which I find really, really exciting. I also, I mean, I want to, in imagination, take it to a silly extreme, because then you might even have like little bits of dark life floating around that we would never be able to see or interact with. It would all just be out there. But okay, that last part is me just getting a little bit carried away. So what I'm hoping to do today is to paint a picture and tell a story about how on earth a mirror world dark sector could help with this Hubble tension thing. Because I think up till now, people listening would just be thinking, this doesn't make sense. How could it possibly be that just by it doesn't seem like they should it all be connected? Why is this mirror world dark sector going to change how fast the universe is expanding? So that's the goal, and we can get started, and hopefully by the end, people are like, yeah, okay, I can kind of see how that happens. I mean, maybe I can paint a quick picture before getting into the main story. Essentially, what it does is by having the dark sector there, it changes the the timing of how old we think the universe is, because the best measurement of how old the universe is for us is the temperature of this cosmic microwave background, of the visible radiation in the universe. Now, if it turns out that there's this dark sector, there's a little bit more of this radiation in the universe than we actually think there is, because we can only see some fraction of it. It's a large fraction, but it's only a fraction, which means that we think the universe is slightly older than it actually is. That the stuff that was there forming the gravitational wells that the cosmic microwave background climbed out of had this other stuff that we can't see now. And the expansion rate of the universe is always decreasing. And so if we get this age of the universe estimate slightly wrong, it's actually slightly younger, therefore the expansion rate should be slightly larger. And this is exactly what the Hubble tension is, that the prediction, given our measurements of the cosmic microwave background for how fast the universe should be expanding, is lower than what we're measuring it to be. So that's the kind of story in a nutshell, and I'll go into more details now. But yeah, it could be that we're getting the age of the universe slightly wrong because we think there's less radiation, therefore we think we've expanded slightly more, and it's because of this mirror world. Why it has to be an exact mirror world and not just radiation, hopefully we'll uncover as we go. Please do, now that I start getting into the details, ask questions on the topic that I'm talking about. If like I'm, especially if I slip into some jargon that I think instinctively is understood, but it's jargon that isn't understood. Up until now, I've been kind of painting a picture, so there will have been some words that aren't yet understood, but the goal now is to fill in those details. So, what is the Hubble tension? Let's start with that. I have Google. Okay, but yeah, Google searching might not be quite as fast as me just and while you're googling, I might be carrying on and stuff like that. Of course, you can play it back later on. So the first thing to kind of talk about with the expansion rate, this Hubble parameter, is that it's not just a speed. I think naively, when you hear expansion rate, you think velocity, kilometers per second, or some unit of velocity, distance per time. But it's not quite that. It's distance per time per distance, which is very confusing when I first say this. But this is actually crucial for the universe to be homogeneous, to be the same everywhere. Otherwise, I think some of the naive questions one asks when one's first encountering cosmology, like, well, if the universe is expanding, where is the center? Where's it expanding from? If it was just a velocity, then yeah, there would have to be some center and everything is traveling away from that center at the same velocity. But if, as you move away, the velocity is increasing, if it's a kilometers per second per megaparsec, where megaparsec is a unit of distance, if as you move to here, the velocity is, say this is 1 megaparsec away, let's say this is 70 kilometers per second, and as you move to here, it's 2 megaparsecs away, it's 140 kilometers per second, then this allows it to be homogeneous, because if you were to move somewhere else, it would also see everything moving away from it. Every point of the universe sees a universe expanding away from it. So that's the first thing, and that's why measuring this is a slightly difficult thing, because as I've said a few times on this stream, not this stream, but on this channel, I guess, the measuring the velocities of stuff is quite easy. I mean, we've gone into it already, like with spectroscopic redshifts, you've done it, and even photometric redshifts, you've got the velocity of a galaxy. If the expansion rate was just velocity, what's the big deal? It's easy, it's trivial. I say this as a theoretical cosmologist who wouldn't, have the first idea how to look for spectroscopic lines, but observational cosmologists are smart people. They know what they're doing. Redshifts are easy. Therefore, velocities are easy. But it's the distance. That's the crucial part that is really, really difficult, because just about anything you might naively think is good for measuring distance, there's subtleties. So you might think, well, how bright is the galaxy? But the galaxy could be intrinsically brighter and closer, but intrinsically brighter but further away, or intrinsically dimmer but closer. And so getting the distance is tricky. So it's always comes down to measuring this distance is always the difficult thing. Yeah. Okay. And then as I was saying, and this is another crucial part for the punchline of the story, it's always decreasing. Now, I can see why that immediately becomes super confusing because I and other cosmologists will tell you in one breath the expansion rate is always decreasing, and the next breath will say the acceleration of the universe is currently accelerating, and you'll be like, "What the hell? What, this doesn't make sense." So it is possible for those two statements to be true if one is more precise about what those two statements mean. So the accelerated expansion means if I take two objects in the universe, so me here and then some galaxy here, or Earth here and some galaxy here, the recession velocities between these two objects is accelerating. If they're far enough away. Andromeda is falling into the Milky Way, but once you get far enough away, stuff is accelerating. Now, if you remember what I just said about the expansion rate, it's kilometers per second per megaparsec, megaparsec being a unit of distance. What that's saying is that if I, here again in my Earth, look at a fixed distance and say the stuff that is, rotate my hand the right way, the stuff that is this distance away, how fast is it moving away? That number is decreasing. But the thing that is at this distance is changing in time, right? Because it's stuff that was closer earlier in time has only just got here, and it gets here at a smaller velocity than the stuff that was there earlier. So the kilometers per second per megaparsec is decreasing, but that doesn't mean that two objects aren't having their recession velocities accelerating. And it turns out that when hello Deanna, I actually have the CMB ready to show at some point in my story. So you've arrived before you were called, but it's good to have you. If I slip anything up, you can correct me. So I was just trying to talk about the distinction at the moment between why the Hubble parameter is always decreasing, and yet cosmologists in another voice can say the expansion at the moment is accelerating. And essentially, it's because the accelerated expansion is between two objects, and the Hubble parameter is talking about the recession velocity at a particular fixed distance, and that number is decreasing. We'll get to the CMB. At the moment, we're talking about how you measure the Hubble parameter locally, and then we'll get to the CMB and talk about why those hot and cold spots help us measure the expansion rate. But yes, this is crucial. So the two crucial things we've come to so far are measuring the expansion rate is difficult because it is kilometers per second per megaparsec. It's not literally just a speed, it's a speed per distance, and you need to measure this distance. Measuring the distance is hard. The second thing is that the expansion rate is always decreasing, which is crucial for, as I told you when I gave away the punchline, if we get the age of the universe slightly wrong because the temperature of the CMB is not the full picture about how much radiation there is, then the predicted expansion rate will be slightly different, and that's what solves the problem in this case. So next I'm going to go into just a few examples of how we have actually locally measured this expansion rate. Velocities, as I've said, are easy. I mean, big quotation marks around easy. Dan is also a theoretical cosmologist, so she won't be able to help here, but or maybe she knows more about this than me, but yes, spectroscopic redshifts are in principle easy. I'm sure that observational cosmologists have all sorts of obstacles to doing it correctly, but they're more easy than distances. So the various ways that we've managed to measure distances are, as I said, you don't know a galaxy is closer just because it's brighter. It could be intrinsically brighter. So you need something that would be called a standardizable candle. It needs to be something where, in some way or another, you can predict its intrinsic brightness. And once you know its intrinsic brightness, you know how far away it is based on how much dimming it is. And the three ways that I've talked about in the stream that is done, there are a few others, but these are maybe the more common ways, are Cepheids, which have a relationship between a periodic brightening and dimming and an absolute intensity of the light. Supernovae, which, because they like build up in mass and then go off at a particular mass, they're standardizable in the sense that they always go off at roughly the same brightness. And based on a kind of intensity as a function of time measurement, you can predict the absolute brightness. There aren't enough local supernovae to calibrate them on their own, so they have to be calibrated against Cepheids. And then there's this tip of the red giant branch thing, which is a little bit more subtle. And there's a video on the YouTube channel now of me describing this in another stream. But essentially, red giant stars can't get any brighter than a certain brightness. So if you have a whole population of red giants in a galaxy, you look at where this brightest red giant is, and that tells you a kind of intrinsic brightness. You can't do it with one galaxy, but you can do it with a population of galaxies. And then you get the distance because you've got that. No, Bo. Let me just share that. The light is always so in special relativity, light always travels at the same speed. So the galaxy is speeding away from you. The light gets a frequency change. This is what happens in special relativity, not a change in speed. And general relativity locally is just special relativity. Locally meaning like if you look at it on very small distance scales. So light is always traveling at the same speed. Is that satisfying, Bo? Or I mean, I worry that going into any more detail than that will require me going into quite a bit of detail of special and general relativity, but hopefully it's satisfying. Where was I? So yeah, so standardizable ruler candles is those examples. So standardizable rulers, then if we can measure stuff on angular scales on the sky quite easily, right? Like if I'm here and I'm looking at the sky, I can see some angle, like how big is a galaxy, or how close are two galaxies to each other. Oh yeah, cool. We should do more shared streams. I mean, unfortunately, our time zones make it a little bit tricky, I guess, Deanna, because you probably don't want to be streaming now because you're tired. And 3 hours ago, I didn't want to be streaming because I was tired. But I guess it's some sort of like 7-ish UTC time zone, we might find a matching time. Standardizable rulers, then. So we can measure these angles really well. But again, we have exactly the same problem. Hello, Asha. If this angle was, we don't know whether the angle is bigger because it's closer or because the distance scale is intrinsically larger. And we don't know whether it's smaller because it's further away or the distance scale is intrinsically smaller. But if we can come up with something we can measure that has a absolute length that we can predict, then we can determine how far away it is because we know its absolute distance and we know what what's it called, what angle we've measured on the sky. So therefore we know the distance. So the best example of that is something called the baryon acoustic oscillations, and they are essentially, this is maybe a little bit tricky to describe before I've talked about the CMB, but they are something I'll come back to once I've talked about the CMB. But they're in the clustering of matter around us. They're the same distance scale as a crucial distance scale that I'll talk about in this cosmic microwave background in a second. Then next thing would be standardizable sirens. So sound waves. I like, this is maybe a little bit of people just being a little bit playful with words here, but people sometimes talk about the idea of gravitational waves traveling through space-time as being the sound of space-time. So a siren would be then something that emits gravitational waves. Paul, yes, good question. Okay, so could I say once more, what aspect is always decreasing? It's literally this kilometers per second per megaparsec thing. The unit of the Hubble parameter is always decreasing. So if I was to look 1 megaparsec away from the Milky Way, whatever happens to be at that distance at a given point of time will be receding slower than something that was at that same distance earlier. But the stuff itself is accelerating as it moves further and further and further away, if that makes sense. There's some exotic types of matter, I guess it's called phantom matter, that would mean that that's not true. And then the long-term fate of the universe would be this big rip idea where the closer and closer stuff just gets faster and faster and faster and faster, and eventually the Milky Way gets ripped apart, and then the solar system, and then the Earth. And but the particle physics side of having phantom matter is a little bit difficult. You get all sorts of inconsistencies, so it's probably not the case that that's the case, but I don't know, it might be. How is that confirmed? Yeah, well, so it's confirmed basically by what I was accidentally kind of answering the question, but maybe it wasn't clear that I was answering that question because I wasn't using wording aimed at that question. But yeah, in order to have it not be the case that stuff at a fixed distance is traveling away more slowly, you would need to have some sort of exotic matter that we haven't yet detected or come up with a consistent theory for how it could exist. So it's less of an observational thing and more of a theoretical thing, that it's not really easy to construct a universe where that would happen. When observational cosmologists do observational fits to data, they do include the possibility that that this expansion rate could be different. But yeah, I mean, it doesn't necessarily fit the data better. So I think if the data started very strongly favoring such a scenario, then the people on the particle physics side, the people on the building the models of how stuff interacts, they'd have to come up with that. Yeah, so naively, gravity is always attractive. So yeah, that's a really good question, Asher. Present on screen. You would have thought that. I presume when you say it slows down, that you mean, yeah, the velocities between two objects as they're moving apart. And for most of the universe's history, it was the case that it was slowing down because gravity is attractive. But this is the whole thing with the stuff that cosmologists call dark energy. It's not the case. Stuff is accelerating in the expansion. And it so happens that, unlike this kind of phantom big rip scenario I was talking about, the accelerated expansion isn't so tricky. It fits quite nicely within a vacuum energy or a cosmological constant, which I don't really have time to go into in a lot of detail today, but it does fit within the theory of general relativity, which is our theory of gravity, and it does have a natural model that would be producing it. So even though on planet Earth and in the solar system and in the Milky Way galaxy, our intuition tells us that gravity is always attractive, it doesn't mean, yeah, like general relativity, the more full theory of gravity does allow for this large distance, uh, hesitate to call it a repulsive force, but tendency for the curvature of space-time to cause objects to move apart at an accelerated rate, which sounds like I'm just like being a little bit uh, like avoiding saying force, but force isn't quite the right way to think about it in general relativity. So it's more precise to say that it causes objects that are far enough apart to accelerate in how fast apart they're moving. Yes, Paul, that's exactly what I meant. I won't share that on screen though. That was just a joke between commenters for people who are seeing this on YouTube. Right. Now, where was I? I was up to standardizable sirens. So this is gravitational wave events. The ones we've measured so far are from colliding black holes or colliding neutron stars, or a black hole colliding with a neutron star. When that happens, there's so much gravitational energy given off that this travels away from the collision as a gravitational wave. Gravity is so weak that even though like a huge fraction of the energy of this collision is given off, like a huge fraction. So I'm sure you've heard of this equation E equals mc squared before, which is saying that mass carries with it energy. And this is how nuclear reactors work, essentially. They lose a little bit of mass and it's given off as a vast amount of energy, which is really, amazing for energy sources on Earth, but also amazing as a kind of fundamental physics law. When two colliding black holes of a given mass collide and then form a new black hole with a given mass, like I'm forgetting the exact numbers, but it's a lot more than, say, 10% of the mass of the black hole is just completely lost to gravitational waves. And that's a huge amount of energy given that E equals mc squared, and C is a huge number. C is like 3 times 10 to the power of 8. So if you have solar mass sized black holes, so 10 times the mass of the sun, and now they're only 8 times the mass of the sun, 2 times the mass of the sun worth of energy has just been given off as gravitational waves. This is just, it's really hard to get your head around how much energy that is. The sun, which is giving off like the most energy that we on Earth can just like imagine. It's ridiculously hot. It's if I'd known I was going to go down this tangent, I'd have looked this number up. But it's energy that it's giving off is actually causing it to lose a little bit of mass. But it's like some tiny fraction. It's like less than 0.011001% or something. It's some tiny amount. And now I'm telling you, when two black holes collide, they lose more than 10% of their mass. So it's insane. But gravity is so weak that in order to measure these gravitational waves, we have to build the most precise like interferometers. So you've got lasers shining on mirrors, and then you've got the sort of one arm this way and one arm that way. It's just clear on the camera. Feel like I'm trying to do some sort of dabbing or something. A bit like that. Should prepare pictures as well. But you've got one laser beam coming along this arm and one coming along this arm. And then because the gravitational wave goes through, they travel slightly different distances, and you measure that. And even though so much energy is being put into this, thanks for popping in, Deanna. Really appreciate it. Even though so much energy is being put into this, you still find it really difficult to measure. Okay, I've gone on a massive tangent about gravitational wave detections. Why is this relevant for the Hubble tension? They're standardizable sirens. So given the waveform of what is measured in, say, this LIGO or Virgo or CAGRA, the detectors on Earth, we can predict how massive the colliding black holes were and how massive the final black hole is based on the waveform, like the actual measured gravitational wave. Therefore, given the intensity of the wave, you can say how far away it was because you know how intense the emitted wave was. There's a little bit of a subtlety that like the angle of the detection relative to the emitting. So you don't just get a perfect distance with one event. You need to have a population of events again. Here, ironically, measuring the velocity becomes a difficult thing because two colliding black holes don't emit any light. And so how do we measure this recession velocity? We don't have spectroscopic lines. We don't have even photometric redshift. In principle, you could measure like the Doppler shift of the actual gravitational wave, but I think that it's just not, redshifts aren't. I'm not sure. Honestly, I'm not sure. I would be speculating. I think it's just simply that the measured frequency of the gravitational wave is not measured well enough that the Doppler shift would be known, or is it? Yeah, actually, I don't know, but for whatever reason, if there was a gravitational wave astronomer, they could tell us. Maybe Deanna knew the answer, but she left a minute too soon. In any case, it's not possible. I can't remember why. And then the problem becomes measuring the velocity because you have a gravitational wave event, but you don't know what galaxy it came from, and therefore you can't do the spectroscopic measurement. So in order to use these standardizable sirens, we need to wait until two neutron stars collide. And then they give off very bright light because neutron stars are made out of matter, not space. I mean, they don't have an event horizon that stops anything from escaping. And then you can say, okay, that gravitational wave came from that galaxy right there. Let's follow up, get a really nice spectroscopic measurement of that galaxy. Now we know the recession velocity. Now we have our standardized siren and our recession velocity. We can talk about expansion rates. So standardizable sirens are the one thing where it's the velocity that's the more difficult thing. I mean, the distance is still very difficult, but the velocity is more difficult. And in 5-10 years from now, we'll have a population of colliding neutron stars that will give us a good measurement of the expansion rate. At the moment, I think we've only got like one event where it was pinpointed to a galaxy, and it gives an estimate of the expansion rate, but it's just one data point, unfortunately. So then there's some things that don't need this kind of standardizing thing, you've got fast radio bursts, which I've gone into quite a lot. It seems like they're the new exciting thing in cosmology. Either that, or they're just the new exciting thing that I've just discovered, and I keep wanting to talk to you guys about because I've just discovered them. But they're exactly what they sound like, short bursts of radio frequency, and so they get dispersed as they travel towards us by charged electrons in the intergalactic medium. So there's a bunch of electrons between galaxies. They're very few, but if something travels for long enough, it interacts with enough of them. And the longer it travels for, the more it disperses because the more it interacts. Different radio frequencies will interact at different rates. And okay, now I'm going to have to clarify something I said to Bo earlier about different speeds. I said everything always travels at the same speed of light. And now I'm about to say that the different radio frequencies travel at different speeds. So let me clarify how I can possibly be saying a true statement twice. So in a vacuum, in the absence of any matter, light always travels at the same speed. When it interacts, it can travel at a different speed. It'll always be a slower speed when it interacts. It will never be faster. And so the radio frequencies interact with these electrons as they're traveling from the distant galaxy to us, and that slows them down a little bit. And the longer frequencies get slowed down more, longer wavelengths, sorry, lower frequencies, and then we can measure that dispersion, and then that tells us the distance. And again, we can measure the recession velocity by looking at some stars in the same galaxy that the FRB came from. Now there's a really cool one, strong lensing time delays. So I don't think I've talked about these in a stream yet, and they're a really, really cool way of measuring the expansion rate of the universe. So if a galaxy is massive enough and aligned with the stuff behind it perfectly enough to us as an observer. So I'm the observer, here's a galaxy, and here's like a distant object, a quasar or a supernova, something bright enough that we can see it from really, really far away. Don't ask me what a quasar is. It's a, yeah, I'm blanking on that. It's a very, very bright astronomical object. But if a very bright distant object and a lens, what am I trying to do that way? Between us is perfectly aligned. The light rays traveling from this distant object to us can be so strongly lensed that you see multiple images. So if this is the source and this is the lens, you can have the light coming around on this side and also around on this side. And this is no different to an optical lens where you can see multiple images, where the light rays are traveling around the lens. Why this allows us to measure the expansion rate, or the distance, again, velocity, easy, distance, difficult. So how this allows us to measure the distance is kind of cool. So if the object that's very distant, that's emitting the light, is somehow varying in time in a way that we can measure precisely, then the different images we see have traveled different distances and therefore arrive at different times in this varying cycle. I mean, it doesn't even have to be periodic. It can just be a gradual brightening and a gradual dimming or something, but they arrive at different times. And so even though we won't know the absolute distance, because again, it could be brighter and further away, or dimmer and closer, we know the difference in the distance. And so if one can model the lens well enough that one knows the different shapes of these two paths, you don't know the absolute distance, but you know the different shapes. Then because you know what the difference in time, because you know the difference in, so then you can model, given a different absolute distance between the original source and the us as the observer, you would get a different time delay between the images. By then measuring the actual time delay, you know the actual distance, because if the time delay was bigger, it would mean that the total distance was bigger. If the time delay was smaller, it would mean the total distance was smaller. So that's really, really cool, because partially just because it means looking at multiple images of exactly the same supernova or quasar. I just find that kind of amazing, that you look on the sky and you see two different bright spots, but they're the same thing that has just traveled around a galaxy in 2 different sides. That's just crazy. Um, and yeah, and then second of all, that you measure the time variation of the signal precisely enough that you can see that one of them got here slightly earlier than the other one. And then third of all, that you model it well enough. So there are a lot of moving parts to this measurement of strong lensing time delays. And so even though there are measurements out there and in the literature and they give values, I think this modeling of the lens is currently a little bit too uncertain to have very, very precise, trustworthy measurements from strong lensing time delays. But it's something that is out there and is good and improving and allows us to measure it locally. David, I thought in quantum mechanics there is no true vacuum, so does light always travel slower in reality? Uh, there's still what one would call the vacuum of quantum mechanics. So it's when light interacts that it slows down. I guess it is still interacting with the vacuum. There then becomes a kind of it almost becomes a question of semantics of if everything. Yeah, I'm not sure. I need to think about that. There becomes a limiting speed. I mean, yeah, I don't know. I hadn't prepared my headspace for answering a question like that. It's a good question. It's a very good question. Let me yeah, let me think about it. I'll try and answer it in a future stream. Really good question, David. Thanks. I'll put it on screen so that people can see what I've been stumped by. He says, I thought, yeah, I thought in quantum mechanics there is no true vacuum. So what he means by that is that um, there is what one would call the vacuum of quantum mechanics, which is the minimum energy state, where you can't extract any more energy, the kind of hypothetical zero temperature. But even in that vacuum, it still has some energy. It's not minimum energy. There's still some sort of fluctuations, and there may not be any particles, but there is the potential for particles to be excited. And so if you have an energetic enough actual particle traveling through this vacuum, it's not completely not interacting. I mean, this is exactly what I was talking about when I was saying things like the Higgs mass gets these corrections. It gets corrections from interacting with this vacuum. So that's what he meant by that question. And I mean, I think that's what David meant. If David didn't mean that, then I'm interpreting a much more interesting question than what he meant. But I think that's what he meant. Yeah, good question. All right. That's all of the ways of measuring the Hubble tension locally that I was going to talk about today. For those who are uncertain, I'm aiming for a 90-minute session, so we've got another 30 minutes to cover the early universe prediction, where we will get to see the CMB. So yeah, how do we predict the Hubble tension, the Hubble parameter? So this is the problem. In case people haven't been following cosmology closely enough, the locally measured value is, say, 73-ish. Do any of my images have it actually on it? Yes, 73-ish, and the predicted value is 67-ish. So that's the problem. It's brilliant enough that these two numbers are actually quite close to each other, but they're now measured precisely enough that there's this tension. So how do we predict it? I've told you multiple ways that we can try and measure it, and the most accurate ways of measuring it are giving somewhere between kind of 69 and 73. The Cepheid supernovae based one is 73. The Cepheid tip of the red giant branch one is more like 69, but the prediction is 67. So there's still a little bit of tension, even if one trusts the tip of the red giant one. And the other measurements are not yet in September 2021 kind of precise and competitive enough. Give it 10 years and standard sirens, FRBs, strong lensing will be super important. But at the moment, maybe not quite yet. And the standardizable ruler, the BAO, depends on the CMB. So it's not an independent measurement of the expansion rate. It's inferred from the CMB, and so it matches what the CMB predicts, but that's not surprising. It doesn't match what the standardizable candidate rules do. But yeah, that. Okay. So we want to predict from the early universe what we think the expansion rate should be today. We use To do this, we use this thing called the cosmic microwave background. I'm not going to show it just yet. Give me a few more minutes. What the cosmic microwave background is light that was emitted in the very early universe. So if I go backwards in time, the universe is contracting. Everything's getting closer together. Everything's getting more dense. Everything's getting hotter. Most of the visible stuff in the universe is hydrogen. If I go back far enough in time, it's hot enough that the electrons and the protons in this hydrogen are no longer bound to each other. Now, at this time, any light that's traveling in the universe will almost immediately see an electron and scatter off it. And then it scatter off another electron, another electron, another electron. It's essentially opaque. You can't see through it. Wherever you are, you're not going to be able to see very far because you're just going to see a photon that's scattered off a very nearby electron. Now let's run the universe forwards in time again. It's gradually cooling. Eventually, at some crucial point of time, the universe cools enough that the light, as it's traveling, will not see a free electron. There's some small period of time where it will travel quite far and eventually see an electron and then scatter. But yeah, this short period of time where it goes from not being able to travel at all to just free streaming forever, it's never going to hit an electron. That light that is emitted at that point of time, as hydrogen forms, as the free electrons bind to the free protons, wasn't microwave frequency at the time, but it is what now, after the universe expanding for billions of years and everything cooling, is now microwave radiation. When it was emitted, it was just the hydrogen line, the ionization energy of hydrogen, which is like, I don't know the number off the top of my head, some tens of electron volts or something, I think. So quite hot, but you know, if the universe was that temperature today, we'd be burnt alive. But thankfully, it's cooled, and it's now microwave frequencies. And your microwave cooks you because it's a very intense microwave. It's not a cooled microwave. Anyway, where were we going with that? So at this point of time, yeah. So okay. So the useful thing about the cosmic microwave background, I think a lot of the time people say it's useful because it gives us a snapshot of the early universe, which is true. But the more interesting thing of it is that it just so happens that in the early universe, the universe was really, really close to homogeneous, to the same everywhere. And people show this plot. This one. Is it on the screen? Yeah, that one. Let's do it full screen. This is not a picture of the CMB. This is a picture of the anisotropies in the CMB. So the red spots are slightly hotter, the blue spots are slightly colder, but the actual CMB has been subtracted from this. So the actual CMB has a temperature of the order of 2 to 3 Kelvin. So it's very, very cold. But the anisotropies in it are of the order of microkelvin. So if I was to show you a plot of the CMB, it would just be one uniform, same color object. These fluctuations are 1 part in 100,000, or 1 part in 100,000, or maybe a few parts in 100,000. They're less than 1 part in 10,000 of the actual temperature. So that is the crucial. How do I put myself back on the screen? That is the crucial thing about the CMB, that its fluctuations are very, very small around some background. And so when one's trying to do perturbation theory, if you have a solution that you know the answer to, which is what we do for a completely homogeneous universe that is completely the same everywhere, and you have very, very, very small fluctuations around it, the maths is easy. It's easy to predict stuff. In the current universe, we don't have that, right? We have something that is statistically homogeneous. It's just as likely there's a galaxy there as there's a galaxy there. I'll put myself back full screen so I can be more clear. But it's not homogeneous, right? Like there are huge galaxies and then big empty space. So it's only homogeneous on average and on very large distance scales. But when the CMB was being formed, because these fluctuations are 1 part in 10,000 or a few parts in 100,000, it's so much easier to predict. And that is the key thing that makes the CMB so useful. It so happens that it's also kind of a picture of the early universe, and it's almost like before the universe got corrupted by all of these galaxies and all sorts of large deviations from the background that make it difficult to predict. And so what that means is that we can predict in a given cosmological model what that CMB should look like really precisely. And that means by measuring it really precisely, we can get really good constraints on the constituents of the universe. And it doesn't matter for any of that the CMB formed early. That's cool, and it's nice to talk about it. But the crucial thing is actually that the fluctuations were very small. Yeah. So what do we learn? I'm going to put it back on the screen actually. So if you look at it, wherever it's gone, if you look at this CMB with me as well, yes, excellent. You might be able to see that this is not random noise. It looks like random noise, but that's just because we don't know what random noise looks like. Random noise doesn't have a preferred scale. And so you would see the hot and cold spots here would have the same, every single angular scale that one looked at, it would have exactly the same likelihood as any other angular scale at being hot or cold. But if I look at this, there are preferred angular scales. For example, this angular scale, no, you probably can't see my cursor, can you? Because I'm not sharing screen. If I look straight in the middle, there's like a kind of big blue coldish region, and then there are quite big red coldish, hottish regions. That's one angular scale that the eye jumps out at. An even more crucial angular scale is it's approximately a degree, which is hard to know what 1 degree is. Like 1 degree being just the normal angular distance scale, angular scale. You've got a 360 degrees in a full circle, but you get, yeah, I'd naively thought I was going to be able to show you with my cursor at this, but yeah, there are little tiny hot and cold spots here, and that that distance scale is absolutely crucial. But yeah, even though you have that specific, maximum fluctuation at that distance scale, all other distance scales also have different amplitudes about how likely it is that there are going to be hot and cold spots. It's not just white noise. And I keep saying distance scale here, but I mean angular scale, obviously, because I say obviously, but I mean it. What I mean is we are looking at the CMB and we can't measure. This is the same problem with the standardizable rulers. It's exactly the same problem. We don't know, and this is the crucial piece that's going to come at the end. We don't know whether the CMB is further away and these crucial angular scales are bigger, or whether it's closer and the angular scales are just smaller, or distance scales are smaller. So the more interesting CMB plot is this one. Um, da, 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 da. And then me back on. Yes, brilliant. Okay, now you see the x-axis is angular scale and the y-axis is temperature fluctuations. So bear with me. This is probably the most important figure in all of cosmology. So it's a difficult one to digest, but we're going to take our time. And once you understand this, you'll understand why the CMB is so amazing. So the red data points here are the measured values of this thing, and then the green line is the best fit cosmological model. So what this is heuristically is when we looked at that, which hopefully will now be small. Yeah, when we look at this map on the right of the temperature anisotropies of the CMB, so not the temperature of the CMB, but the anisotropies, and we kind of average over this angular scale and say, when we look at fluctuations on this angular scale, are they bigger or smaller? And a smaller one would be closer to zero. Like if the fluctuations were completely random, they'd be zero. And if they tend to be bigger, like if the red and blue is bigger when you look at it on this angular scale, it'll be bigger here. So this 1 degree scale, which are the little tiny little hot and cold spots on this map, is where the biggest peak is. Now, what this distance scale angular scale corresponds to is called the sound horizon. It is the distance sound waves in this hydrogen plasma traveled before the CMB formed. And the reason why you get a big bump at that scale is, imagine you have in this primordial hydrogen plasma a bunch of different slightly overdense regions and slightly underdense regions. Now, the ones that are an overdense region that is exactly the right size, such that from the beginning of the Big Bang until now, until the time the CMB is forming, it's just long enough that because it's overdense, stuff's falling into it and it's contracting and it's contracting and it's contracting. Now, eventually, if the universe just carried on and the hydrogen plasma carried on, the pressure inside this contracting region would get so big that it would start to push apart. Because there's hot radiation, photons traveling around, and electrons repel each other, it would eventually just be this pressure and it would push apart. But there is one distance scale where just when the CMB forms, it had just managed to reach its maximum density before it would have pushed itself apart, but then the CMB forms. These hot spots and cold spots will be the hottest hot spots and the coldest cold spots. And that means that at that precise angular scale, you'll get this peak. Then there'll be some other distance scale where it has contracted and then expanded and was just about to collapse again because the pressure's dissipated and the gravitational pull is about to pull everything back in. Or if you'd started out in an underdense region, you had made it out and then all the way back in, which corresponds to the second peak. And then the third peak is the regions that had gone collapse, out, back to collapse. And then the fourth peak is collapse, out, collapse, out. So you're going to smaller and smaller angular scales here. See, this is big angular scales. Well, I keep pointing at this with my cursor, but you get what I'm talking about. As you move to the right, you're going to smaller and smaller angular scales. Okay, I'll answer some questions. Sorry. Yes, Paul, that would be amazing. Such a thing does exist. I'm going to have to go through all the comments of this afterwards and make notes of cool things to show in future things. I don't have that handy, and because I've only got 20 more minutes, I won't look it up. But yes, this present on screen would be amazing to sort of get the picture that I'm talking about now very clearly shown. Like you could only keep the 1 degree fluctuations and show that map, and then only keep the 0.2 degree fluctuations to show that. Those do exist. David, why macro Kelvin squared? Is that just to make them all positive numbers? But if not, why not just use absolute value? The answer to that question lies in the technicality of what this plot actually is. It's showing heuristically what I was describing, but it's not what I was describing. What it actually is it's the magnitude squared of the Fourier coefficients of a Fourier transform in angular space of the map, and there it is. Magnitude Kelvin squared, because if you took the average without squaring these coefficients, the average would be 0. If you just took the absolute value, it would not have quite as easily calculated statistics. I think you could in principle just show that, but it wouldn't be as easy to model statistically. Why not take the square root of what is being plotted here, I think is a totally arbitrary question that, you could plot the square root of this and then you just have a slightly different looking thing. I mean, one thing that there's a few subtleties in this plot. The x-axis, sorry, y-axis has actually been multiplied by L times L plus 1. So angular scale, if you look at the top of the x-axis, it says multiple moment L. So this L is, I'm not going to go into the details, but as L gets bigger, angular scale gets smaller. But you see the L goes from 2 to 2000. So the y-axis has actually been multiplied by L times L plus 1. If you didn't have that multiplication, the large distance angular scales would be way, way higher, and the small angular scales would be way, way lower, and the plot wouldn't look as interesting. So for interests of brevity and stuff, I've had to just sort of say heuristically it's showing how things are looking on different angular scales, but in reality it's not exactly a plot of that. The final punchline that the shape of this curve allows us to predict or infer different ratios of how much matter there is to how much dark matter to how much radiation to the expansion rate at the time this was formed is all true no matter what the y-axis happens to be. But yeah, the small scales have been amplified here, and it is temperature squared, not temperature. But those things aren't crucial to the punchline. So yes, this first peak at 1 degree is the distance scale, or the angular scale, at which fluctuations have just managed to compress before expanding. So the idea I wanted to get across by talking about this plot for a little while is how much information is in it. So first of all, the location of this first peak, the angular scale it happens to be at, is telling us about relative ratios of the hydrogen to the radiation, that if there's different amounts of that, the sound will travel at different speeds, the pressure will take longer to build up or build up more quickly. So that's telling us stuff about how much ordinary matter there is, how much radiation there is when the CMB is forming. These second and third peaks are absolutely crucial. Hello Veda. As I was saying, the second peak is not the parts, the angular scales where a collapse has happened and it expand and then another collapse. It's just the collapse and expand. Yeah. Sorry, Veda. I do go over like itemized things for the first 10 minutes so that people who arrive late can catch it, but I guess not for the first 50 minutes. But yeah, feel free to ask some questions if you want, or yeah, obviously watch the stream back. So yeah, the second peak is stuff that's collapsed and then expanded. And equivalently, if it had started off as an underdense regions, it's expanded and then collapsed. The crucial thing is that the hot spots are getting amplified into hotter hot spots or into colder cold spots by the time the CMB forms. Now, why are these second and third peaks carrying so much information? The dark matter that is present in the early universe doesn't feel this pressure. It just falls into all of the parts of the universe that were initially slightly more dense, which means that it amplifies this first peak and amplifies the third peak, but doesn't amplify the second peak, because the second peak is the stuff that's collapsed and then expanded. And then the third peak is the stuff that's collapsed again. So the relative heights of these second and third peaks are telling us the relative amounts of ordinary matter and dark matter. So even by just looking at these first three peaks, you're starting to see how we're starting to learn how much radiation there was, how much ordinary matter there was, how much dark matter there was. And then you get how this decaying of this curve that happens in the smaller angular scales is then to do with photons diffusing as the CMB is forming, having more than just one scattering, having multiple scatterings. So that's also telling us about relative amounts of matter and ordinary matter and radiation. I've only got 10 minutes left, so I'm not going to go into all of the other bits of information in detail about what we've got here, but neutrinos and how much neutrinos there are subtly shifts the relative locations of these first, second, and third peaks. Lensing of the CMB as it travels through the universe changes how these smaller scale peaks, how sharp they are, or it smooths them out. There's so much predictable information in this curve that we can extract because, again, these temperatures are tiny. It's microkelvin of an object that has a temperature of Kelvin. So it's like 2.7 Kelvin or something is the actual temperature, and the units here are microkelvin. I mean, it's 4,000 microkelvin squared, but if you were to work out what that is as a ratio of the actual 2.7 Kelvin squared, this is still a really, really small number. 1 part in 10 to the 5, 10 to the minus 5. It's a very, very small fluctuation. And so it's very predictable. And yeah, I'm running out of time to go into lots and lots of details about what information is here. But even from what I've just said, you can get a picture that by the precise heights of these peaks, the precise locations of these peaks, the relative heights of these peaks, you're learning about how much matter there is, how much ordinary matter there is, how much radiation there is, how fast the universe happened to be expanding at that point of time, how much it got lensed by local stuff as it traveled towards us. Yeah, that's it, David. 1 part in 100,000 present on screen. Thanks for doing the maths. Now, because I have to, I'm going to show you. I think I said this is the most impressive plot in cosmology. I was wrong. This now is the most impressive plot in cosmology. Let's just get rid of everything else. This is me. I want not me. This is the polarization in the CMB. The same kind of on angular scales things. You see the x-axis is L here. They don't have the degrees here. I'm going to talk about this in another stream, I think, because this, yeah, I want to get to the punchline. Yeah, it does look very similar, and it has peaks at kind of the similar angular scales. That's crucial. Yeah, one could talk about this plot for a whole stream, or not a whole stream, but for quite a while. And I'm just going to say there's no a priori reason, if one didn't believe in the Big Bang, why the polarization, why the CMB should even be polarized. Second of all, if it is polarized, if you took the intensity and averaged it on these angular scales, that you would have something that's even predictable. And then third of all, that prediction, again, you got blue line here as the theory prediction, and red data points are the measurements. There's no reason why it should be so precisely predicted. And I think the units here are even smaller. I can't see it on my screen, but they're an order of magnitude smaller. So instead of 1 part in 100,000, it's now 1 part in a million. So this is just insane how well this is being measured. And I think if someone out there is like, these cosmologists don't know what they're doing, I've got some alternative model, the Big Bang didn't happen. Like, if you can tell us why the cosmic microwave background has these fluctuations in temperature that look like primordial sound waves through a hydrogen plasma, and that this light is then polarized in just such a way that when you average the intensity of the polarization on these angular scales, you get these blue line, this blue line, then great, you have a model that can challenge the Big Bang. But if you don't, then you have to appreciate how unlikely it would be that if the Big Bang was wrong, that this is what you would be seeing. There are only 6 or 7 parameters that go into predicting these lines, and there's so much more information in these lines than 7 pieces of information. There's the locations of these peaks, the heights of the peaks, how high they are relative to each other, how fast they decay as you go to smaller angular scales. All of this has to be predicted by your model, and is predicted by the Big Bang, plus this lambda CDM, cold dark matter plus dark energy model. So it's just crazy good that yeah, okay, Paul, I'm probably going to have to go over 90 minutes to say this, but yes, this is the crucial and important thing, and this is what the paper I wanted to talk about. I can't share my screen to show you the paper because it'll just get blurry. This new piece of this new idea that managed to do this without throwing everything else out of whack. So yes, let's now get to that punchline. I wanted to wax lyrical about the polarization for a little bit, but let's move on now. But you've hit the nail on the head, in that this is why solving the Hubble tension is so bloody difficult. Because naively, yes, you could just say, I'm just going to revise the distance and age, and surely that solves everything. But it doesn't, because you'll throw everything else out of whack, and you don't manage to get the exact same brilliant matching. So there are models of what is called dark radiation out there, where literally that's all it does, is it says there's some extra radiation in the universe that we can't see. And that's all it is. It's just radiation. So it changes the expansion history of the universe. Now, as I was saying, these are all angular scales we've measured in the cosmic microwave background, not distance scales. So yes, in principle, you could just say we're a slightly younger universe. The angular scales are therefore slightly smaller distance scales, because we're looking to a close, it's not quite as far away as we thought it was. It's, instead of being out here and a certain angular, get myself on camera, out here and a certain angular scale, it's actually much closer here, and a same angular scale, smaller distance scale. The problem with doing that naively is that, yeah, the ratios of things like the total amount of radiation to the total amount of matter to the total amount of dark matter then gets thrown out of whack, because you've added radiation, but you haven't added new hydrogen and new neutrinos and new dark matter. So Yeah, well, the dark matter part's less important here actually, but because you could just add new dark matter. We haven't actually measured local dark matter well enough that you can't just kind of rescale that a little bit. So this is the new insight essentially, that if you have a mirror universe, now you are not just adding radiation, you're also adding all the other constituents as well. So instead of just kind of throwing everything out of whack, you're literally just saying, to a certain extent, it's the same universe, the same total amount of baryons. There's just some visible baryons and some dark baryons. Total amount of light, just some visible light and some dark light. Same total amount of neutrinos, just some neutrinos that will interact with our neutrino detectors and some that won't. And then that means that when we look at how much radiation density there is by measuring the visible CMB, we aren't getting it right. But when we then rescale the age of the universe, we don't throw everything out of whack, because yeah, all these ratios are all still the same and correct. So yeah, actually that punchline part isn't so complicated to articulate, and that would be fine if that was the full story. Unfortunately, there's one absolute scale in this problem other than the temperature of the cosmic microwave background. Yeah. So hold on. We've measured the temperature of the cosmic microwave background, so therefore we can say, assuming that there was only in this primordial hydrogen plasma, there was only the visible hydrogen and not the dark hydrogen, we can estimate the age of the universe. When we now add this dark stuff, yeah, it changes how much we estimate the age of the universe. But what it doesn't do, I've only got 2 minutes. It doesn't change. Yeah, I don't know if I want to go into this in great detail. The problem becomes, and I'm just going to say it and maybe articulate it in a future stream, or maybe go for an extra 10 minutes. I'll see how I feel. Is there's the as I told you, this CMB forms when the photons in this hydrogen plasma can travel far enough without bouncing off an electron that they can kind of essentially travel forever. What this depends on, the time that this happens, depends on the density of free electrons, which is decreasing in time, right? Because the electrons are getting bound to all the protons, and eventually shrinks below some crucial value that the photons can travel freely. If I kind of do this trick of saying there's a dark mirror world, and I rescale all of the densities of the universe without changing the predicted temperature of the CMB today, because I'm only adding dark stuff, I'm not adding more visible stuff, and therefore increasing the temperature of the CMB, and therefore getting the right expansion rate because the universe is slightly younger. I haven't changed this free streaming length. I haven't changed this prediction for the number density of electrons either, but I need to. And so I think if it wasn't for this flaw, like, this would be a super compelling explanation of the Hubble tension, to the point of, I think people would be jumping on it and being like, maybe this is the explanation of the Hubble tension. Yeah, you have to postulate a mirror universe, but it's just they only have one parameter, which is the like density of this extra stuff, which turns out to be about, I think, a tenth of the density of the visible stuff. So it's not much of the dark matter; it's a tiny fraction of the dark matter. But you just add this, and it kind of fixes everything, except for this one other problem. You have to also rescale the density of free electrons by the same amount, and there's no compelling reason why a mirror universe would cause that to happen. So the mirror universe would cause us to get the age wrong, but it wouldn't cause this other parameter to change. So yeah, what essentially happens is that you replace your Hubble tension with a, like, they in the paper, I think I actually did link to the paper in like my very first comment of this thread, but if I didn't, I can link to the paper after I've finished the stream. Then this they get around this by changing some even earlier universe thing, which would change the like abundance of these electrons in the early universe from when kind of protons form out of quarks and gluons and stuff. Yeah. Thanks, Paul. I should try and wrap up super quick. Um, the and what? Okay, so I'm just gonna have to say it. This causes a change in the abundance of helium, and it's very opaque why changing the abundance of helium in the primordial universe will change the amount of free electrons, but it does. So this model essentially replaces the the Hubble tension with a primordial helium abundance tension, but it's an interesting insight that you can do this rescaling. Previously, people have thought, oh, we just have to add more radiation. But then, as I think Paul um, intuited, that's going to cause a mess because you're changing all of these ratios. So these guys were like, well, what if we just fix everything by having all of the right amounts of everything? And then the one missing ingredient was that you need to change the density of electrons in the early universe, which I guess, stay tuned. Maybe 6 months from now, some clever group have worked out how to do this changing of the zero of time with either not a dark mirror sector, or if they do have a dark mirror sector, that dark mirror sector somehow mimics the behavior of having slightly more or less electrons in the early universe. I think I'll wrap up now. So just to summarize that whole story again, we've measured the local expansion rate by measuring these distances and getting the velocities. It's some value in the low to mid 70s, 73-ish, or 70, somewhere between 70 and 73 perhaps. We predict it using the lambda CDM, dark energy plus cold dark matter plus ordinary matter cosmological model, and it comes out to be about 67. It's miraculous that over such an extrapolation that we get the right value, like close to the right value. We predict it from the CMB by measuring these angular scales and looking at how they relate to predictions of what this early universe should look like by plotting that angular power spectrum that I showed you. If we got our zero of time just slightly wrong, we would think the universe was slightly older than it actually is, and therefore this always decreasing Hubble parameter should actually be slightly larger. If we just did that naively, we would mess up all the ratios. But if we do it by having an exact replica universe full of dark hydrogen, dark atoms, dark electrons, dark neutrinos, it would fit the data wonderfully, apart from this one problem with the electron density in the primordial universe. So yeah, that is very insightful, but it's not the solution to the Hubble tension. If it is part of the solution to the Hubble tension, it would mean that we do have dark galaxies, dark planets, dark stars floating around inside the universe. There wouldn't be a dark solar system literally where we are, but there would be a dark group of stars floating around in the Milky Way doing what normal stars do, but just emitting light that is not the same light that we can see. It would have all the same physical laws as our stuff, but it would be different. So that's the story. Thanks everyone for coming. Let me if you're still watching, then obviously you like what you're seeing, so please do like, subscribe, share, support. I think share is the crucial thing. If you like what you're witnessing at this stage, the most important thing you can do is tell your friends and about it, and share it on social media and all that sort of stuff, so that other people can see what's going on. Yeah, the preparation, even without graphics, takes time because I have to think of the whole story I'm going to take and make sure I understand things. So I hope you appreciate it, and see you again. Maybe next week, or if not, then in a couple of weeks. Thanks, David.